Hey, so while I'm getting set up, I just flew in from New York, and boy are my arms tired. But my electric razor decided to stop working on the way here. It has a lock on it, which I've never known it to have, and I've never been able to get it unlocked. So how many hackers does it take to turn on my electric razor? We're going to find out. So if you would like to take a try, it is right up there in the front. If you get it to work, I will give you a bag of swag. I'll mail it to you when I get home. But seriously, it's got one button. It doesn't turn on. It's fully charged, and it has a lock icon on it, so you can figure it out. So I decided to have a fun talk. Originally, I wanted to speak about how our business at Trailbits works or changes when the risks get high. But over time, it kind of evolved into this talk of, well, it seems that some of these things are a bit easier on one side of the fence than they are on the other, and I wanted to explain why that is. So the title of the talk today is, What the Blockchain Got Right? No, Really. This is a field that Trailbits has been working in for quite a number of years, and we find it exciting because the consequences are high. People legitimately lose hundreds of millions of dollars because of simple coding mistakes they make in little things called smart contracts, and there is a widespread ecosystem of tools and knowledge and techniques that have been applied to make some of these things, not all of these things, secure in a way that I have never seen on regular software. So a little bit about Trailbits. We're a 10-year-old software security research and development firm. We work in a couple of really neat fields. We do things with cryptography, modern cryptography, things like multi-party computation, zero-knowledge proofs. We do high-assurance software and like satellites, trains, and airplanes. We do work on cloud-native software that run multi-billion-dollar unicorn tech startups. And we do work in blockchain security for the reasons that I mentioned before. We build software for people. They hire us to write prototypes for security tools and security products. We audit software. We find security vulnerabilities and weaknesses and help people write better code. And then we also do fundamental research. We end up getting contracts with DARPA, the Army, the Air Force, the Navy, to fundamentally advance the field of computer science and write tools and develop techniques that can make software better. All of these end up combining really well in this weird blockchain space, which you'll learn why. So Ethereum. If you don't know, Ethereum is a system that lets you write smart contracts. There are these little autonomous finance bots that receive transactions, and they manipulate global state. That's essentially what they are. So it has a bit of a reputation, right? They're tiny little programs that evolve in consensus. You can do really complex financial activities with them, like create tokens and do credit default swaps, and you can integrate them into browsers, but they're built with the shittiest version of JavaScript that you could ever design. And the community itself is not so into security. So most of the time they get hacked, and it's for huge amounts of money. So you can see this is a quote from a team that got hacked, and they asked, hey, why did you get hacked? Like, what did you do to not get hacked? And their answer is, well, a month ago, I asked my team member to reach out to somebody for auditing, but we kind of forgot. Like, as we approached launch and we pushed back the date a few times, it just never really popped into our head, and we never audited. So we just kind of forgot, and then we got hacked and lost a lot of money. It's like, that's the starting point, right? Like, this is the field that you're all reading about. Internally, the way that this stuff works is that it's a shared global computer, right? So there are people with the ability to send inputs to contracts, which are finance bots on the right. And the bots are only different because they have code processing the transaction, where the people just have a human clicking the buttons. The neat things about it are that you can see every transaction that happens. The whole computer thing is transparent. And the other neat thing is that you can send input from a person's wallet to any finance bot anywhere. And there's like nothing that anyone can do to stop you. To any contract or account. It's very fun. The finance bots, they're programmed in this language called Solidity, which is targeted for like JavaScript developers that started out with Node or web developers, because the field is really desperate for developers, and that seemed to be the easiest way to get them. It's only a few years old, first languages like C++, so Solidity came around when Ethereum did. Ethereum was 13, 14? Can't remember. So there are languages like C++ or whatever that have been around for 40 years, but Solidity has kind of like taken a lot of modern learnings about security, even versus a language like C, and thrown them out the window. Like, they unexpectedly changed the order of operations, right? Like the ability to take like two numbers and add them together or whatever, like that is different in Solidity than it is in every other computer language you have ever learned to code in. I don't know why, but Solidity as a whole is kind of a language that has evolved rather than one that has been designed. It doesn't really have a good sense of like where it is and where it's going. It's just like got cobbled together. And if you think that was bad, right, it actually is worse than what I'm describing. So here are like two little code snippets that I like to use to give an example of why this language is so bad. So the for loop on the top overflows if foo has any greater than 32 elements. That's because var gets declared as 8 bits. So don't use var when you declare a specific type, or else you will have catastrophic issues for seemingly perfect code. And then the one on the bottom is what the compiler produces when you try to use the number, whenever you try to use like 0 or something. It just takes like 0 and exponentiates it to 256 for like absolutely no reason at all. So a regular compiler would obviously just optimize those things out instantaneously and just give you the value that you're looking for. But, you know, we're dealing with billions of dollars here, so of course the compiler does not do that. Like, there's no consequences whatsoever for a poorly functioning compiler. And the language itself, I kind of alluded to this, but they've managed to reinvent every vulnerability class that has been eliminated from modern languages. Null dereferences are exploitable conditions in this language. There is no other language invented in the last 10 years that has exploitable null dereferences, right? So a null dereference, that's when you access like what's at 0. And what happens to be at 0 is the owner information for contract. So you can do a null dereference, you can change the owner of the contract, cash it out. So it's not only exploitable, but it's maximally exploitable. So you could steal all the money based on that. So it's just completely psychotic, right? Okay. But let me drag you back down to earth. The expectations here are that the field will be littered with easy bugs, that analysis of this will be really tricky. It's this weird arcane language. There's this goofy stack machine thing. The language doesn't make any sense. So confidence in these systems will be impossible, right? That's the expectation. When you talk to security engineers, everybody always says, well, if we could just fix the languages and the compilers and the frameworks, there wouldn't be any foot guns for us to step on, and all our code would be secure. But the reality is that it's actually far different than that. I encounter some of the most secure, actually no, the most secure code that I have in my career while reviewing Solidity. And it's insane because despite all of the extraordinarily insecure compilers and languages and frameworks and all the foundation upon which everything is built is trash, but the code comes out as inherently testable. So they fix it in post. And with that extremely testable code, we get clients of ours that come in the door with high coverage property test suites, with symbolic execution rigorously applied to an entire code base. There is even a robust network of suppliers for symbolic execution as a service. There's like 6 different vendors that you can choose between. That is not something you can do when you're developing software on any other language, right? So this actually, having everybody come in with a suite of correctness tests, having everybody already adopted rigorous static analysis, having everybody having adopted property testing, that is kind of what we want the rest of the industry to look at. So despite all of these terrible, awful parts of Ethereum, there's a lot here that we actually want to copy, that we want to understand how it evolved so that we can hopefully replicate it in other places. Now, you could ask why, and I think a lot of people will give you very naive answers why. They can say, oh, code is law, that like, you need to be right the first time, and there's no recourse if you're hacked. And like, that's fine, but I don't think that's the case. That's not what created the system that I'm reviewing. People also say that because it's worth a lot of money, that it evolved in this way, that it's inherently testable, that lots of resources have been spent securing it. But, iPhones are in a billion people's pockets across the globe and manage extraordinarily sensitive information on behalf of all of you. Apple has invested billions of dollars in making them secure, but they are much, much less so than a good smart contract. So there's a lot of systems that are out there that actually do have more money invested, that carry more risk, but that end up in a worse state. So the outcomes here for the small amount of money that actually has been applied to make them safe are actually phenomenally good. The reason why, I don't know if anybody has heard this joke, but there's this old joke about a dairy farmer who's trying to keep up with the agri-conglomerate down the road, and he asks a physicist for help. The physicist goes back to his lab, and he works really hard, and he comes back weeks later, and he says he has a solution, but it only works on spherical cows in a vacuum, right? Because that's how physicists are. That is generally how reading papers from like ACM, CCSS work out. When you read these academic ivory tower papers, they're all dealing with spherical cows. They always deal with like core utils, right? Like every single damn paper has found all the vulnerabilities that exist in the ls command, right? Wonderful. But the weird thing is that on Ethereum, they only support spherical cows. That is everything you deal with. Everything you deal with is a spherical cow. So in reality, it turns into this field where the spherical cows, the extremely limited runtimes, are the perfect opportunity to apply software testing research. So the rubber meets the road in this field in a way unlike any other. It's really weird. Okay. So let me go backwards a little bit. We'll do a little computer science lesson. There's some really contentious stuff in this section, but we will have a nerd fight about it later at the bar. It is a keynote, so chill. What is a program? All right, abstract. What is a program? So a program is essentially like, well, let's not even say that. I'll try to avoid the harshest of fights here. But basically, input changes the way a program behaves. There's some input that comes in, which I've defined as this little grid. Those are all the different potential inputs that can go in. The red one is the one that we've chosen. And then it hits this state machine where stuff bounces around or not, and then it exits, right? That is a program to me. So the input state could be a lot of different things. It could be like standard in, it could be networks, it could be, whatever, it could be different kinds of input. And maybe the program stops and maybe it doesn't. Maybe it gets stuck in a little loop. But most of the time, let's just say it does. So in that case, if you wanted to then as simply define security is the combination of two things. It's, say what? Oh, crap. Shut that off. Thank you. So security is really the combination of two things. You're trying to find the states that are bad and the inputs that cause them. That is it. That is security in this version of things. For instance, so like an assert will tell you that you encounter something bad, but it won't tell you the input that reaches it, right? So as we have constrained time here, let's only dig into number one. We're going to talk about inputs. Because inputs are something that typically an after-the-fact security engineer can control. Whereas usually as a security engineer, you can't go in and like rewrite the whole program to figure out and change the way that it handles state. But you can usually test it for input, which is why things like fuzzing are such a big deal. So again, simplified, this is kind of what testing looks like in this simplification of security and simplification of programs. On the left, we've got like unit testing and fuzzing and like other kinds of testing where you pop out holes in the input as fast as you can possibly do that. So that would be things like, or rather, in the unrestricted case, that's kind of like where a program starts, is you might have some unit tests, they exercise a few of the inputs. Sometimes there are unexpected inputs that are off the place that you expect inputs to come from, like environmental stuff. Sometimes people forget. System calls can sometimes be controllable, those sorts of things. And that's what you're dealing with when you're given a program and told to make it secure. On the other hand, there are two techniques that you've got to secure this, right? Option one is you can reduce the size of allowable input. So those are things like having a typed language versus a static one. That means that there's a lot of less kinds of input that can be given to your program. Or you could delete code. Or you could separate privileges. You could carve out huge amounts of code and lock it inside of a sandbox somewhere that's unreachable from the outside of the program. On the other hand, you could test your input. And this is what most people fall back to because they don't have the ability to radically change the way a program works when they are doing an audit of it. So you might write unit tests that pop out individual boxes. You might write fuzz tests that populate large sections of it randomly. Or you might write formal tests. You might use techniques like symbolic execution that will wipe out an entire row or a column or a quadrant and make it all red. So side note, mitigations don't fix code. They just limit the impact of failure if you're asking where those live. But with this in mind, let's talk a little bit deeper. So there's a maturity process that I think people go through when they write software. The first step is they get this very young kid, college guy kind of episode about code. Or actually, this is really the pointy-haired boss version too, where they want to write secure code. So they say, well, we're going to train all our developers. We're going to do tons of code reviews. And everyone's going to be the smartest person on the team or ever created. And we're going to just understand tons about C++. And we just won't write any bugs because we try really hard. That's basically what it comes down to. And it absolutely does not work. It's kind of like this, have your existing programmers work harder in the same amount of time. Computers are extraordinarily complex machines, and the ability for a single human to even manage all the operations going on in their head for what they're writing is very limited. So it doesn't work, right? Phase one is, well, maybe we should test a few things. What do we want the program to do? Let's make it do that and see if the outcomes are what we wanted. And that's kind of unit testing. So they have the input space, there's some points on the grid, and the unit tests only test things that developers know what they might not know. There's not that many of them compared to what the program can do. So developers are kind of blind to what they don't know. They're only testing things that they know to test. So this is kind of the better part of most software shops. If you are at a developer conference, then a point of pride might be hey, how are you testing your software? How much coverage do you have? And developers will talk to you as a point of pride. They'll be I have 80% coverage, and it's so wonderful that my job does this. They'll put it on a job advertisement. If you apply for a job, they'll say benefits, has tests, right? That's how important this stuff is to regular people writing regular code. But for obvious reasons, asking a developer to enumerate all the bugs in the program and then write tests for them is not a good way to write secure software. So then you've got people that progress to phase two, which is fuzzing. They're So everyone that uses these, they say they're amazing, right? I've never talked to a person, if you give a developer AFL and let them use it for 5 minutes, nobody ever comes back and says, I tried these and they sucked, right? They always come back and they say, our Lord and Savior AFL, we will now bow to this program that I have discovered. It is extraordinarily useful once they get here. It's also something that's getting a lot more acceptance by academics. They've realized, hey, these things get picked up. So you can see 30 different versions of academic papers that try to optimize the test generation process for AFL, right? Those are very popular nowadays. And then you've got the kind of end game, which is to test every input. It doesn't give you perfectly correct software, and you have to ask, who verifies the verifier? But you could just not be verifying all the inputs because you didn't realize what the total space of the input was, right? So beyond these limitations of the testing techniques and beyond a broken verification tool suite, sometimes you just get inputs that exist outside the space of what you expect, so you still find bugs. That's the little thing floating on the corner. But it's still pretty good, right? It's strictly better than not doing anything. Obviously, we've got far better coverage than any previous stage. So this is a goal. This is a place to work towards. But most people reject it as impractical, right? Like, I don't know of a lot of hackers on the flip side that would tell you that, oh yeah, like I predominantly use symbolic execution, or I predominantly use abstract interpretation, or like whatever technique. So today, the state of the industry is that most people are at phase 0. The people at phase 1 are bragging about it. The people at phase 3 are spotted across the industry, but it's not consistent. At Trail of Bits, we did a really interesting study where we resurrected the first available fuzzer ever made from 1989. It fuzzed a bunch of Linux programs, and we got that fuzzer working again in 2019, so 30 years later. And then we resurrected the code that was fuzzed in 1989, because a lot of that stuff is still present in modern Linux. And we ran the fuzzer again. Let me tell you how many bugs we found, right? We actually redid that for Microsoft. We took a famous Microsoft fuzzer from, 1999, and then we reran that on the current modern version of Windows at the time. I think it was Windows, it was either 7 or 10, and it still finds bugs, right? So even in an extraordinarily rigorous shop like Microsoft that's fully adopted an SDLC and applies fuzzing on every single little code increment that all their developers make, not good enough, right? Like they are not applying it consistently. So that brings you to phase 3, which is usually just disregarded as wildly impractical and nobody ever tries it. Now, there's a reason for that. And the reasons for that are actually easy to identify. So why are we stuck? The reason why we're stuck is that developers don't create testable programs, yet the testing tools we have require them to be. So all the programs that you want to use, let's say Manticore, we have a symbolic execution toolkit that allows you to rigorously test software, but it can't model real system calls, right? That's something that I wrote. Like it can't figure out how to do uname. The nice thing about blockchain software is that you have to make it testable by design. So regular software is hard to make testable. Therefore, most of the testing tools just don't work. So there's a couple reasons why this happens. So unit tests, a lot of times when we look at programs that are written in like traditional languages, you get a unit test, but the unit test has like 2/3 of the code in the file creating some kind of contrived environment to set it up. That's an indication that software is not really testable. On the other hand, there's lots of functions that have side effects that change how other functions work. So if you have something where you can kind of prime the pump and you send it a few network packets and it changes the internal state that the program is in, you're going to get different results testing that than the program that wasn't primed. That global mutable state and the fact that these things are moving targets and have changing dependencies, changing runtime environments, changing operating systems, make it a moving target to hit even when it's not a production application. So at a high level, you have really bad abstraction boundaries. Let me change this, where the cursor go. Can't see what I'm talking about. There we go. So at a high level, you have really bad abstraction boundaries. Most people are like, let me see here, like maybe it's a yeah, so the Unix philosophy lost, Linux philosophy run. Functional code isn't really a thing. People aren't writing pure functions, they're writing object-oriented code. People aren't really breaking programs into smaller ones. But if you do that, if you have smaller programs, then you can turn integration tests into unit tests. You can turn a dumb fuzzer into a property-based testing suite. If you can take a large program and break it down and clearly identify the connections between those different components, then you can start to do things like slightly less impossible verification. So at its heart, kind of this global mutable state problem and the complexity of interactions between components is the root of all evil here. The other problem that we have is that software isn't generally made to be reproducible. Not reproducible in terms of like when I compile the code, it's exactly identical, and then I can do these like supposedly find the backdoors that the bad guys are inserting. Not that kind of reproducible. But more that I can't tell you how many times I've been on an audit where I've been given a code base and they don't even expect that I'm going to figure out how to build it, right? Like the build system is created by some guy in like a dark corner of the room that manages this arcane build system with all these special commands and like a 30-page PDF that you have to go through to produce this exquisite software artifact that works for that guy's machine. And then they tarball that up and ship it. So Docker has only really become a thing in recent history, and it's not widely adopted yet, I don't think, given the number of pieces of code that I've seen. In general, builds are a mess. So we outsource all this logic to really unpredictable environments. We're deploying to different operating systems. There's no version dependency tracking. Even if you're doing something that's more declarative, like people have these manifests where like cargo or whatever can select the version. Still people have like lots of unlocked dependencies. This is where you see in JavaScript world, people get hit by like shift left and all that junk. And then network calls, like any kind of interaction with the user ends up changing that state, which then prevents you from rigorously testing that application, because it's been primed somehow. Really good example here. We have a tool called, KRF. I believe it's called a kernel rootkit fuzzer. I forget what it's called. But we wrote KRF. It just munges the output of system calls to your program. And I cannot tell you the number of programs we've killed, that we've exploited, or that we've broken somehow by doing that, right? So a lot of this stuff is just like not reproducible, and it doesn't behave the same under these different conditions. And the last thing is that the input space is huge. So programmers don't really know what changes stuff later in the program. They're not, they expect everything to be referentially transparent. That like, if I evaluate f of x, then I always get y. But that is very frequently not the case. They assume that a system call always returns as expected, but sometimes somebody's running KRF. So if you're, another really fun one is that if you're in like Computer Science 101 and you have an algorithm with like 10 different nodes and you make a type with a label for each node, then some people make their node IDs a string type, and now you have white space bugs. So this over-reliance on dynamic input and not statically typed input vastly explodes the input space into all kinds of things that you would not expect could be sent to your program that you now have to deal with. So there's not really an effort to make input space manageable to even adequately test it on the part of most software engineers writing most software. I would like to forget that nulls exist. I would like to not see code that is extremely typed just pervasively across the entire ecosystem. List and tuples are really nice, but in fact they sabotage the ability for your code to be secure. So we try to do research at Trilobits. Like we try to use papers, we try to apply them to software, but it's pretty tough for us. Like we're willing to tune stuff up. Like we will write a makefile, we will write our own compatibility layer, we will try to do the minimum possible to get the stuff to work. But papers are not designed for software that works for real. At best, they work on core utils, which is not what comes in our door for us to audit if you had questions. And being able to reproduce the results on software we work with is just not happening. Yes, and we have a really good, there is a really good blog post we have called How to Spot Good Fuzzing Research, where even the minor improvements that people make to things like AFL that already exist are not framed correctly and misrepresented. So we have a great summary of a paper from a former employee called How to Spot Good Fuzzing Research that walks through kind of the minimum bar required to say that your fuzzer is better than somebody else's. And when you empirically evaluate that against all the papers that are out there, so in a review of 32 fuzzing papers, there's like one that passes the bar. So we don't even know what we're trying to improve. So, end result, we can't speak to the safety properties of any code that we review, and we can't produce any evidence that it's safe against some class of bug. We are kind of just stuck because of this, because of these poor abstraction boundaries, because the input space is huge, because the software is not reproducible. We are stuck in this endless cycle of, well, let's just pull some bugs out of the hat and report them to the client, and they got their 20 bugs for this audit, so they'll be happy, and we can come see them next year. But what does that mean about the software that they've reviewed, or that I've reviewed? What does that give them? Does it mean that they're safe? Does it mean that they're not exposed to a certain class of issue? Does it mean that the software won't fail under X and Y condition? Like, no, we don't know what that means. We just know that it's incrementally safer than it was before, not that it is actually safe for any intended purpose. So the assumption is the code has bad bugs and we don't know where. Which brings us to the blockchain. So with that as the state of software, we can kind of look at blockchain for a glimpse of the future, right? It's this weird kind of engineering that literally does not support the obstacles we've encountered in other software. And I need a drink. So essentially the question here is, if the people at ACM CCSS win, what do they get? Like, what does workflows look like when you're able to apply research easily? When you can test programs and try these techniques with no effort? Blockchain ends up being a really good test case for all these different software testing research methodologies. And the clear question is, if brown cows make chocolate milk, do spherical cows make data dots? Ooh, okay. So, okay, great. So in a smart contract, it's weird because this complexity, these poor abstraction boundaries, massive input space, these issues that stand in the way of us creating testable software on regular code, they actually have incentives against that. And that is where the incentives matter. Not that code is law. The incentive is that it costs money to make code size big. It costs money to process large inputs. So you have this incentive to produce compact programs. On the right, that's the visual disassembly from a tool we wrote called Ethersplay. That's a smart contract. That's how much code you're reviewing. Every single state change is a transaction. So the abstraction boundaries are extremely clearly defined. And you have to pay for every single little object that you use. And because you have to pay to even execute code, you have to terminate. So you don't have to worry about getting caught in a loop somewhere. Like at some point, smart contracts end, which is crazy. So this whole class of issues that you learned as little Dan and 19-year-old computer science 102 about the halting problem or whatever, just screw it. Not important, right? We've solved it with gas. So these abstraction boundaries, like I said, they're very, very well-defined, and all the software runs in a completely homogeneous environment. There is one blockchain, everyone shares it. You don't need to figure out if your dependencies correctly match production. You don't need to worry about the operating system. You don't need to worry about your build system. Everything runs on the same blockchain. So anytime there are state updates, you're using transaction data, and it's really small. The state variables that process it on the side of the smart contract are also tiny. They're usually less than 10. And the approximate numbers to kind of demonstrate scale is you're dealing with hundreds of bytes or thousands of instructions. And if you're doing that, all of a sudden these heavyweight analysis techniques are possible. You can use symbolic execution everywhere when you're only dealing with programs that are 1,000 instructions long. So from a back of the envelope math perspective, they're in a great place to start. And this leads to weird results that you wouldn't expect. Like me starting in this field a couple years ago, I would not expect that symbolic execution is quite possibly the most common analysis technique in the space, and that there's widespread understanding of it on the part of software developers writing tests for code. Just wacky, right? Even writing the symbolic execution engine is easy. It's a weekend project. A lot of people maybe took on these ridiculous challenges as a college student. They try to write a brainfuck interpreter over a weekend. And there's only a handful of instructions for that, except they're all white spaces. But it's easy, right? And then you're like, oh, wow, that was really fun. Symbolic execution is really powerful. I'm going to try and write this for x86. And you try to do it, you immediately fall on your face. Because x86 is extraordinarily complicated, and it'll take you years to write a really good one, which we have done, right? Us and Anger and a few other folks have spent extraordinary effort trying to perfect these exquisite symbolic symbolic virtual machines that process languages as complicated as x86. But EVM, the Ethereum virtual machine, is still something you can kind of do in a weekend. There are less instructions. There are less side effects. It's like something that you can kind of just whip together, and it actually works. And like you can use it to find real bugs. And it's not that hard to use. When it comes down to it, we've seen amateur developers take advantage of symbolic execution in ways that I would never expect a developer on like a web application or a compiled code application to do. So of course, like experts can do more with it. There's more that I or Trail of Bits can do with symbolic execution than like a random person who picked it up yesterday, but still, it's really cool. Oh yeah, and in this field too, it's also wacky. There are places you can go where you can just copy and paste code into like a web application, press enter, and the Symbex will run on the back end and just like give you results, right? Again, so just like, this is bizarre world. Fuzzing is also exceptionally popular across the space. In the right environment, the correct option can be easier, right? These kind of testing techniques are widespread because they are easy to use. The hardest part about writing a fuzzer in this environment is being able to execute the code. You have to, in general, all the fuzzers that I'm aware of for Ethereum have a built-in virtual machine, a built-in EVM that emulates the code, so they deploy internally to themselves, run it. And the hardest part is actually just finding where the errors are. In a normal program, finding an error is easy, right? Like, what does an error look like in a C++ program? Segfault. Easy, right? What does an error look like in a smart contract? Fuck if I know. Like, you have to figure out what the program actually was intended to do, and then identify those cases. So the hard part is actually writing these invariants, or these specs or properties that you're actually setting out the fuzzer to look for. So that's kind of limited to your knowledge of the system and to the documentation that you've been provided. Writing some detection for when things go wrong is a little bit hard, but not unsolvable. But anyway, again, here, when an environment is testable, it's easier to do the right thing. So a lot of these tools do exist. They are quite easy to apply. You just have to get over the initial hump of, well, what am I trying to find? So you write some invariants. But that ends up being a lot better because there are actually invariants that you would care about a fuzzer to find in C++ code that go beyond segfaults, but most people never make it there. Everybody usually sticks with segfaults because they find an ever-increasing and never-ending number of them. So you never think about, well, what kind of application-specific fuzz test results might I care about? It's not a question that enters into most security engineers' minds. And then there's static analysis, which is basically the same as ever. It's more popular than fuzzing, less than symbolic execution. It is an undergrad class project yes. Gonna have to skip a few slides. So you could start with your like undergrad quality static analyzer that's like grep with extra steps. And as long as you, you could just write some analyses that look at writes to state variables and do like some really basic data flow and bam, you've got bugs. Like that's it. It's really simple. The hard part here again is writing a bunch of heuristics. So we have done that. We've written essentially over the last 2 years half of a compiler that will take Solidity, translate it to an SSA form, and then perform extremely sophisticated analysis to find hundreds of types of bugs. But again, this was the effort of like a single person over the period of about a year or two, and we've got this extremely effective static analysis toolkit that is unheard of for a language that's not Solidity. So big picture, code correctness tools work most places. The developer experience is basically /find bugs. And we can find truckloads of issues. So at one point we actually had to make a giant spreadsheet, like a Google Sheet, just to track all the fuzzer results that we were finding, running these tools across all the code on the blockchain, which is again visible, so I can run my analysis universally across the entire ecosystem with the press of a button, which is also nuts. So generally, when developers become aware of these tools, when I present at blockchain conferences, they close Telegram, because that's what blockchain developers use, and they run the tools during our presentations about it and come up to me afterward and say, I found a bug before your presentation was over, right? The neat thing about this is that people who are taking it seriously are getting really, really good We have people come to us with these high coverage symbolic test suites that cover just a vast amount more state space than any traditional software company ever has. We had Gemini is a great example. Like, I can't say they will never be hacked, but they have invested the right things to make sure that the billions of dollars they manage in a smart contract won't show up on Web3 is going great by Molly White, right? And the level of verification that you see on that kind of code is the same level of verification you'd see on software running on a satellite of somebody making a cryptographic library, and it's respectable. So this is the money shot. Smart contracts are actually the ideal way to develop software for many different versions of ideal. So now I'm going to have to skip a section because I didn't practice this talk or time it. So I'll just give you the cheat sheet a little bit about how Trail of Bits approaches these things. Because obviously, like, we work in blockchain software. I work in regular software too. People hire me to do audits of software that are not Solidity, thank God. But we have to have a process that produces these more uniform and more rigorous results. Because I don't like to test software the old way. I don't want to just stick my hand in the bucket, pull out a bunch of bugs, and show the client, like, hey, this is wonderful. I found 20 bugs. And they're like, well, what does that mean for me? And I say, I don't know. There's probably 20 more. Like, see you next year. Like, that sucks. I don't want to do that. So a lot of what we do is we find that the most important barrier to overcome is the reproducibility part. As an auditor, I will spend sometimes extraordinary effort to make builds reproducible. Reproducible to me means something different than I think the rest of the industry means. But like, I want to build the damn software. I want to build it on a modern compiler. I want to build it with a build system that I can instrument. And I want the ability to routinely and comprehensively and repeatedly run these more rigorous analyses to drop out bugs. I want it to run on a modern compiler. I want it to run in an emulated environment. I want it to run, like, for example, we haven't talked about this much, but Zoom hired us back in April 2020 when they were having some issues. And when we got in to work with them, I had a team of 8 people that were ready to work for 3 months to find bugs in their software. The very first thing we did is we rewrote their entire build system for their entire code base from scratch in 2 weeks. And then I let everybody go audit it for code because I wanted the ability to do things like ASAN. I wanted LLVM's compiler analyses. I wanted libfuzzer to be available to me because those allow me to produce measurable outcomes instead of just essentially, like, we could have easily started that engagement, not done that precursor step, and then just found bugs from all over the place forever. And they would have thought our productivity was insane. But in this case, we helped them help themselves because now you empowered every other developer on the entire development team to use those analyses. And once you kind of lock in the state that you'd like with some of LLVM's tools, you can make sure they're not backsliding with new commits. So once we have those build systems rewritten, Trail of Bits also has a monumental proprietary code base of bug classes that only we know about. Yeah, surprise. I share a lot, but I don't share everything. So we have semgrep analyses, we have CodeQL analyses, we have Slither analyses that we are kind of incubating internally that we've discovered from past assessments that we can apply instantaneously to know that code base is not affected by flaws that we've already discovered before. And then as a last resort, semgrep is amazing because it doesn't use buildable source. So if I can't get that build system working, that's my go-to tool. And then we go through this process where there are 2 steps now. Instead of just doing a manual audit, we have another team of people that are dedicated to reading documentation, to interviewing developers, to reading code to extract out security properties, encoding them in a tool that finds them programmatically, and then committing that to the code base during the engagement. So that at the outcome of a project, you're getting invariance with programmatic tests. You're getting property tests that cover more, sometimes all possible inputs for a given scenario. You're getting negative tests that don't depend on any hard-coded value. And you're defining new failure modes for fuzzers and small executors based on what the developer actually believes should be true about the program. So security properties can then get tested on every commit. We have a whole bunch of GitHub actions that allow people to take advantage of these that we've published on the GitHub Marketplace. For when we do audits, that's the end of them, is take the code we've given you, install the action, run it forever, block the build if anybody breaks it. And we're going to skip the case studies. Okay, so 3 slides left. I know I'm a little bit over time. So languages are getting better. So there's some bright spots here, right? Like when I look at is traditional, I hate saying it this way, but is traditional security on a path to better itself? And the answer is kind of yes. I see a couple of bright spots that I'm optimistic about, where I won't be solving the same problem 3 years from now that I am today. Dynamic types are dying. If you take a look at the languages that are popular, that developers want to use, they are basically all statically typed, which is amazing, right? Because I think a lot of the dynamically typed ones are usually marketed as like beginner friendly, but even the ones that are really beginner, like Python or whatever, Python's getting types, right? Like there are systems now that layer them on. People have realized they're important. And people have also started to realize that it's easier to write code when you actually care about pure functions, when you're not trying to manage all the incredible side effects from running a piece of code. You're going to write a pure function. And package managers are getting reproducible. Things like NixOS and Cargo and virtual env and Docker are now much more popular today than they were in the past, which makes my job so much easier. So here's the actual data. That's from Stack Overflow's developer survey from about like 3 or 4 months ago. All the popular ones typed, all the other ones not. So that's kind of the shift in the market that you're seeing that shows that actually maybe we're going to have an easier job a few years from now. And yeah, reproducible environments. So like being able to deploy is nice. Like I don't want to depend on a 30-page PDF written by a guy that's never seen the light of day to compile a piece of software. And now I don't have to because I have GitHub workflows and I have Docker and I have virtual env and like always kind of hoping that somebody shows up in my client queue with NixOS as their package manager. When it works, it doesn't just help me, it also helps their developers, it helps their QA, and it helps their production. So there's more than just security that is pushing things in this direction. It is not just us in this room that can be loud about, hey, declarative package managers. Developers want them too. There's a symbiosis. There's like overlapping needs here that are being satisfied by something that benefits everyone. And the one like weird thing, this is the second to last slide, the one weird thing that I see that could change a lot is WASM. When I think about a lot of the properties that Ethereum has that are beneficial, I see many of them reproduced in WASM. It doesn't have undefined behavior, kind of, if you're not dealing with floating point. It limits external interfaces, makes them easier to test, and it has smaller self-contained programs that are easier to run. So you can kind of think of WASM as like a well-specified virtual machine with safe defaults. If this becomes more popular, which I hope it does, then we can unlock a lot of these benefits of software testing and research in the kind of software that all of us run all the time. So that is it. I have some references here for some of our blockchain work. It's so like offensive that we took it out into a separate GitHub repository called Critic. Some people don't even like to look at it. But our blog has great research on applied software security testing. Our publications repository is an archive of all the talks like this we've ever given. And obviously we're looking for people that want to join us on this journey. So if you're tired of just kicking applications really hard and like beating it up with your fists and being happy with it, and you'd like to use some knowledge from the future to test things, then come work for me, because we have lots of software that we apply research to in a way that you wouldn't expect. And that's it. So email me if you've got any questions. Thank you for having me.